Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Alison Farrish with us today. Hey, Alison.
Hi, thanks for having me.
Oh, well, thank you for being willing to talk about your really lovely article. Let's see. Let's start off. Where are you located at?
Yeah, I'm in Houston, Texas at Rice University. It's in the 90s today, as it usually is this time of year.
Was that the temperature or the humidity?
Both. Yeah.
Yeah, it's a good old Gulf moisture.
Yep.
Yep, and that Gulf moisture actually seeps up into Phoenix. That's what this is when we get our monsoons, and it's all driven by the Gulf moisture coming up. And then probably it's September 7th, 2021. It's probably in about a month or so that'll start sliding back to the Gulf, and we'll go back to the usual desert, dry kind of weather. So, so what's your position there at Rice?
Yeah, right now I've finished up my PhD recently, earlier this spring. So right now I'm a postdoc with the Rice Space Institute.
Cool.
Kind of wrapping that up soon as well, before I move to Goddard Space Flight Center in the fall.
That is awesome. Very good. Well, congratulations on finishing, Dr. Farrish.
Thank you.
That is so awesome. And on your upcoming move to Goddard, I think that's awesome. Very nice. Very cool. So Alison, what do you like to do for research?
Yeah, so my PhD has focused on how we can kind of help solar and stellar physics inform one another. And I'm particularly interested in the applications to exoplanet habitability and discovering interesting exoplanet systems. So that's the broad strokes. My thesis advisor, David Alexander, is a solar physicist through and through. So we've been taking a lot of the kind of tried and true solar physics techniques and trying to push the boundaries into how much they can tell us about stellar physics and how they can inform kind of exoplanet environments, the way the sun informs, our environment at Earth.
Nice, very good, cool. And that is going to bring us to this very lovely APJ article, Modeling Stellar Activity Rotation Relations in Unsaturated Cool Stars. And Alison, take us away.
Yeah, so like I said, this was done with my thesis advisor, David Alexander, as well as another professor here at Rice, Christopher John Scroll, who's an excellent observational astronomer and was really bringing in that kind of astronomy side of things to our sort of solar physics-based approach. And additionally, Minjing was a lovely undergrad we had visiting from China a few summers ago. So it was great to have her on board as well.
Nice.
Yeah, so I mean, maybe the title is the first thing to talk about. So we want to model the stellar activity rotation relation, and I'll talk about what that means, as well as looking at unsaturated cool stars, and I can get into that as well. But we want to kind of understand how stellar rotation impacts the amount of stellar activity you get from that star, and in turn, what that might mean for the associated exoplanets. And we're looking at this class of cool stars, which are stars like the sun and smaller, because we're kind of interested in solar-like behavior in exoplanet systems.
Okay.
So this is a modeling study where we've taken a solar flux transport model and using what we know about the sun and other stellar activity relationships, applying that to other cool stars. And particularly in this work, looking at the relationship between X-ray luminosity versus what we call the Rossby number. It's a measure of solar and stellar dynamo activity. So looking how energetic emission from a star is a consequence of rotation, basically.
Nice. Okay.
Yeah, I guess moving along. So the Rossby number is kind of the key parameter here. So in the intro, there you can see that it's the ratio of the rotation period to the convective turnover time. So sort of a comparison of the time scales of how fast the star is spinning versus how much interior plasma is roiling and bubbling, basically.
Okay.
And when we talk about unsaturated stars, we're talking about stars with a Rossby number greater than about 0.1.
Okay.
So increasing Rossby number is less active, actually, because that rotation period gets longer and is therefore essentially a less active star. And it's a really useful quantity for discussing magnetic activity or stellar dynamo action.
Mm-hmm.
And the other important thing I would say is that this unsaturated regime is kind of a well-known in stellar observations as a regime where, as the Rossby number increases, the X-ray luminosity goes down. So a less magnetically active star is less active in X-ray luminosity in its corona, basically. Which makes sense, kind of why that would happen. A less magnetically active star is less active in the energetic emission it puts off. By contrast, there is a saturated regime where at a certain Rossby number, about 0.1, more rotation basically doesn't yield more energetic emission.
Okay.
And why that might happen, why there is that kind of ceiling, is the subject of a lot of other research that's kind of not what we're getting into in this work. But I think maybe moving on, I can talk a bit about the modeling approach we took here.
Okay.
So we're using a surface flux transport model to simulate emergence, evolution, and decay of magnetic flux on the stellar photosphere. So it's an empirical model based on decades of solar observations. It was developed by Carl Schreiber and his colleagues, and we've worked really closely with Mark DeRosa at Lockheed Solar Astrophysics Laboratory, who was an author of the code. And it's a really lightweight computational tool to kind of model over long time scales, so over decades or over multiple stellar cycles,
Okay.
and to be able to visualize how magnetic flux is emerging and evolving on the surface of the modeled star. And it's a really nice tool that I've used quite extensively in my PhD thesis. In an earlier paper in 2019, we were looking at a range of these modeled stars with different Rossby numbers, and basically looking at how we can incorporate things we know about stellar activity from observations and sort of build out these robust models of stellar activity over long time scales.
Okay.
So a few of the kind of equations we use there are on the screen there. One is that we know from observations that the cycle period is tied to the rotation period. This is the subject of a lot of ongoing research campaigns. It's not easy to observe stellar activity cycles unless you're looking at the star over decades. The sun's activity cycle is a period of about 11 years. So when looking at other stellar cycles, we're biased towards the short ones. So actually drilling down on what that relationship is the subject of ongoing studies for sure. That equation 2 there is relating the average flux on the surface to that Rossby number, which is itself related to the rotation period, as well as there's a factor of the stellar radius there. So that's how we're kind of parametrizing the magnetic flux properties by this Rossby number quantity.
Okay.
And then finally, the flux transport model relies on differential rotation and this meridional, so poleward flows of the flux on the surface. So this is this equation 3 is from a dynamo model. We can't actually we can't observe scales, the scales of like individual flows on other stars. We don't resolve those.
Right.
But with some modeling, there's some suggestions that the meridional speed would be kind of inversely related to that rotation or that cycle.
Yeah.
So these are just some kind of parameterization of different aspects of the magnetic flows that are based on what we know about other stars. And here we've incorporated them into the solar-based model. So we can build out kind of a whole suite of modeled stars. And you can see that in table 1, I think on the next page, that we provide a range of different Rossby numbers with the different flux associated, the equatorial rotation speed, the cycle period. And what's interesting is that, for the very most active Rossby number of 0.1, kind of getting up to that saturation limit, the cycle period is only, 2 years. Those are very active stars with very short cycles that are easy to observe. Okay. As you get to lower Rossby number, higher Rossby number, less active, I get it confused too. So it's always good to drive home. The cycle periods get longer. The equatorial rotation speed is smaller. So there's a lot of interrelated parameters in what determines the magnetic flows on the stars. So
let me ask, so these are the input parameters, and then what is some of the output that comes out of the SFT model?
Yeah, so for interested folks, can refer back to the 2019 paper by myself as well, where we kind of showed the proof of concept of this model with all of these, stellar physics parameter relationships built in. So what you get out is, so the output is the magnetic field distribution on the surface of the star.
Okay.
At that time step, over the iterations of the stellar cycle. So
it's a time dependent code. So over time, you watch the evolution of that.
Yeah. Yep. Exactly. Yeah.
Okay.
And with the cycle modulation built in, so there are stellar minima and stellar maxima, and that's kind of an important aspect of this work, was that we really wanted to include that cycle modulation of the stellar flux concentrations over time, because that's what makes it's what makes the observable output from the star a time dependent quantity as well.
Okay, thank you.
Yeah. So I think maybe figure 1 is interesting to look at as just kind of some of the first output of this model with the relationship to X-ray luminosity. So this is the range of runs that we described in table 1 with those input parameters. And you can see the Rossby number going from about 0.1 to about 1. We have some added extreme cases on the end that we included here just for completeness sake. The actual Rossby number of the sun itself is not known super accurately. So this being a solar code, we know that we're scaling up and down, making the sun more active or less active. And that's why everything has to be scaled to kind of solar parameters. But I think we show later in this work that this is kind of an appropriate approach even for other stars besides the sun, which was one of the more interesting results of this paper.
Okay.
Is
the X-ray luminosity an output of the SFT code, or do you have to take the magnetic surface fields and then convert
Yeah.
that post-process?
Yeah, great question. So yeah, exactly, the second one.
Okay.
The SFT outputs the magnetic structures and the magnetic flow, magnetic strength. And then we're applying here a relationship from Petsov's 2003 paper.
Okay.
You can kind of see, I think just below this, somewhere on this page, yeah.
2003.
LX is a function of that unsigned magnetic flux on the surface.
Got it.
And that was, that's an interesting paper on its own. And Christopher Johns Kroll, who's a co-author on this paper, worked on that paper as well.
Nice.
And they took a look at a range of solar features, observed features on the sun, so X-ray bright points, individual active regions, the full disk, and then they incorporated other, dwarf stars as well, and found that there's this really robust relationship over, 12 orders of magnitude between the magnetic flux and the X-ray output for the sun and for sun-like stars, basically. So that's a pretty robust relationship between the magnetic features that we can simulate and the anticipated X-ray output from those stars.
Okay.
So the other thing I'll point out about figure 1 is the vertical spread is a consequence entirely of that cycle modulation of each of these stars.
Okay.
So it looks a little funny it's in these silos, but those represent at each Rossby number, there's a star that we've modeled with that Rossby number, and its magnetic output is time dependent. So its X-ray output is time dependent as well.
Got it. Cool.
So this is just setting the scene in figure 1. I think if you move along,
Okay.
we wanted to take a look at, so here we wanted to take a look at the not just the raw X-ray output, but the X-ray output as a function of volumetric luminosity.
Right.
Because in the literature and in a lot of other observational studies of real stellar populations, folding out the mass dependent quantities, which are essentially the volumetric luminosity, and then Rossby number is a mass independent quantity as well. You can kind of compare big populations of different stellar types more directly. And so we wanted to take a look at X-ray luminosity as a fraction of the volumetric luminosity for direct comparison with observational studies.
So it's small, right? 10 to the minus 4, 10 to the minus 5.
Yeah. Yeah. So this figure 2 is just taking a look at solar volumetric luminosity values from a kind of standard solar model. Since we're starting from a solar-based the solar-based flux transport model. So just in this figure 2, all we've done from figure 1 is divide by the volumetric luminosity that the sun would have had at that time in its past when it had that Rossby number. So the sun spins down over time, as do all magnetic stars. And in the past, the sun would have been brighter and more magnetically active. So here it's just dividing out that volumetric luminosity over time. So this was just kind of a proof of concept of that. There's a few issues here. One is that the sun is one star that has a finite lifetime, and we're only halfway through it. So it kind of narrows the range of Rossby numbers we can look at. So you'll notice this is a more narrow range in Rossby number than the previous plot.
Right.
And again, this is just taking solar values, and we wanted to really see if we can discuss stars other than the sun, stars that might stars of other stellar types that we know have exoplanets around them. So this is a good thing to check, but then we wanted to move into how can you actually produce this kind of plot, but for other stellar types as well.
Yes.
Mhm.
I'm with you.
So yeah, we're kind of building in a bunch of different facets of stellar evolution as we go. So this here is kind of where it's getting more interesting to me anyway, was we then wanted to build in that volumetric luminosity evolution with Rossby number for a few different stellar types. So luckily this work has been modeled by other groups, particularly this Yale Potsdam Stellar Isochrone project. It's called YAPSI. You can see it in the caption there from Spada et al. And this is really great work that kind of has modeled how different stars with different initial mass functions evolve over time, how their convective rollover time changes as the inner shells burn and the convective zone actually gets smaller over time as a star ages. So the internal physics of the star are changing as it ages, as well as the spin down and the changes to the magnetic flux on the surface.
Okay.
So what we've done here basically is for a few different masses, so an F star, a G star, a K star, and 2 M stars, one that's before the partially convective boundary and one that is fully convective. For each of those, we've taken a look at that volumetric luminosity over time. And the interesting thing about the partially convective and fully convective M stars is that the sun is partially convective. It has a rigid radiative core surrounded by a convective envelope. And the surface of the sun is kind of where magnetic flux bubbles up from that convective zone. But we think, the sun generates its dynamo largely at the boundary between that radiative zone and the convective zone. That's the subject of lots and lots of research, how exactly that works.
Indeed.
Yeah, but so it's interesting to think about, partially convective M stars, K stars, and F stars. They're probably all similar to the sun in that we know they have a radiative core and a convective envelope. But what happens when you get to that fully convective regime at the very low mass stars? Do we expect that their surfaces might still act similarly to the sun? That's a big question in exoplanet studies right now, because it's much easier to find Earth-sized planets around the smallest stars. So exoplanet host stars that are the really small M stars are pretty interesting to people right now, because that's where we see Earth-sized planets in habitable zone orbits. So basically what we've done here is now expand just from looking at the solar case to incorporating evolution of other stellar types and looking at how their X-ray, their fractional X-ray output might change over time. So there's kind of 2 interesting facets to this figure 3 here. One is that you can think of the x-axis as the very long time scale evolution of the star over its lifetime. So an F star, for example, as it spins down, would follow something like that green track. As it gets less magnetically active, it will have less X-ray output over millions of years, billions of years.
Yes.
But the y-axis is the short time scale variation, just on that stellar cycle time scale. So, 5 years, 10 years.
Okay.
And I think that's what makes this figure 3 pretty interesting to me anyway, is that we're incorporating the short time scale variation, which would be relevant to, individual space weather storms on an exoplanet, as the host star becomes more and less active over the cycle. And we're incorporating the long time scale variation. How would the star be impacting the evolution of the climate over millions of years?
And so the highest X-ray luminosities, flares and all, are from the fully convective mass models. They sort of form the outer envelope of this suite.
And what's interesting about that is because they're the dimmest stars, so their volumetric luminosities are much smaller. That comparatively, that X-ray output is a larger fraction of the total output. Right.
Somewhat paradoxical, but yes.
Yeah, but I don't know. Interesting implications for climate models for Earth-sized planets around M dwarfs. Yeah, that kind of thing.
Habitability.
Absolutely.
Yep.
Very
nice.
So all of this is still kind of theoretical, and hopefully I've motivated why we built in some of these different evolutions over time. But I think the most interesting part is figure 4, where we've actually just compared directly to stellar observations in this figure. So Wright et al. 2018 was the culmination of a few observation campaigns from that group at the Center for Astrophysics in Boston. And this is where you can actually see the saturated regime is those gray dots that kind of flatten out at Rossby numbers less than 1. Yes. And we don't attempt to model those because we know the sun is not in that saturation regime. So using solar tools and pushing into that regime would be maybe something to look into in the future, but it wasn't what we were attempting here. Yeah. But you can see our modeled fit in red and the observed fit from Wright et al. 2018 as the black dashed line. And this is a statistically significant agreement between the two. And we had to quantify that a bit, but they're essentially describing the same behavior here. And you can see our between figure 3 and figure 4, we've taken a random sample of all of those points in figure 3. Because we wanted to mimic, when you're looking at a set of stars in the sky, they're randomly phased in their magnetic cycles. There's nothing saying all of them would be at stellar maximum at the same point, and in fact you wouldn't expect that. So we wanted to see if you take a random sample of all the modeled stars at all times, it should mimic how we observe populations of stars in real life. And we find that it does, both in the slope, which is encouraging because we've built in what we know about magnetic evolution over time, but also in the spread, which is interesting as well, because in our model data, the spread only comes from that cycle modulation, with a little bit of the spread coming from the difference in stellar types as well. But we can fully explain the spread in the model data, and we think that that is encouraging that it matches the observed data as well, that we think that these stars are probably all have some kind of modulation over short time scales due to cycles. The other interesting feature I'll point out, and you kind of touched on it, is that I've labeled the fully convective stars that were randomly sampled, and most of them fall above the trend line. I mean, that actually was a feature in the Wright et al. 2018 data as well, that for the few unsaturated fully convective stars that they looked at, they tended to fall above that trend line as well. So I don't know that I'll go so far as to say anything super profound there, just that that's a feature of the observed populations that we captured in the modeled data as well. And I think it does have to do with that X-ray luminosity being just a comparatively higher fraction of the total brightness for those dim stars.
Nice.
Yeah, I think that's all the key points.
Okay.
I think it's interesting that we know the model very well, and we know kind of the assumptions, and a lot of them are solar-based assumptions. But when you compare to stellar observations of F stars through fully convective M stars, we essentially reproduce most, if not all, of the features in the observed data that we expect. So I'm kind of happy with this work. I think it has a lot of good implications for being able to take solar physics modeling tools and look at how they can inform exoplanet studies, how they can tell us how exoplanet host stars might be impacting their associated planets. So
Nice.
yeah, I think I'll stop there. Thanks.
Awesome. Well, thank you so much for walking us through your really lovely article here. And you touched on it a little bit toward the end there. So let me go ahead and ask, where do we go, let's say, over the next 5 years? What's the next couple of steps in this kind of modeling? Is there does one anticipate long enough baselines to catch cycles on other stars? And so would there be an evolution of the SFT model to ESFT for exosolar or other solar OSFT model? But just sort of, where do we go over the next, let's say, 5 years or so?
Yeah, great question. I think one is, there's not a lot of data on low mass M stars or fully convective M stars, whether most of them have cycles, and so that's certainly something that I think there are observation campaigns now looking for cycles of M dwarf stars, and particularly we want to look for the more moderate or low activity stars. We generally have the idea that those will be more hospitable for exoplanets, but it means they're less magnetically active, so their cycles are longer. So it's very easy to find the most violent stars, and to characterize their cycles, but we want to look for some of the more moderate activity. So that's certainly something that I think just will come with time. It's just, you need 10 or 20 years of data to see if there's a cycle there that's and
the appropriate in the appropriate telescopes, or that'd be ground-based, space-based.
And then, so in terms of where this kind of modeling might go in the next few years, there's a lot of really great work being done in solar dynamo modeling. So that's one thing about this surface flux transport, is it doesn't contain any information about the interior. It's kind of an empirical treatment of, if you assume there's a black box that's putting flux onto the surface, how does the surface evolve once the flux emerges, which is what makes the code lightweight and kind of easy to do lots and lots of runs and things like that. But marrying that to what are the actual complex processes going on in the solar interior is a whole field of its own. And certainly how that might be happening on other stars is something that is a big question as well. I think it's as hard as it is to do solar dynamo modeling, it's even harder to do stellar dynamo modeling, because we know so little about the actual 3D structure of the field on other stars. It's difficult to resolve. There's been a lot of progress in what they call Zeeman Doppler imaging, so being able to resolve magnetic features on stars, on other stars. There's been a lot of progress in that already, but that will be something that, as we know more about the actual structure of magnetic fields on other stars, that will change, I think, how much we can learn about these stars. Yeah.
Cool. Very nice. Very nice. Alison, thank you once again for sharing your very lovely article.
Sure.
And that'll do for this one. And I hope this made your astronomy day just a little bit better, everyone. And we will see you on the next one. Bye-bye.
Thank you.
Whoop.